Welcome to our webinar for our CarTrain high voltage battery, so diagnosis and maintenance of high voltage batteries. At my side again, Daniel, good to have you here.
Good to be back. Been here with Lucas-Nuelle for 15 years, a couple of years here in the automotive department.
My name is Chris. I'm the head of the Digital Experience Learning team, and we are the hosts of the webinars for Lucas-Nuelle. So this is why you will see my face pretty often during all the other webinars. We have seen in the webinars before the brand new CarTrain, which his team has developed, which is diagnose and repair of high voltage vehicles. But today we make a deep dive more or less into the heart of an electric vehicle, which is not the electric motor, but the high voltage battery, right?
Exactly. So we're going to have a look today at our CarTrain here. So high voltage battery diagnosis and maintenance. So again, we're going to have a look at not just how the system works, but some of the repairs that you can do on a high voltage battery, but understanding how to make those diagnoses as well. So this system has been around for a while. It's actually, I think, launched in 2017. So a little bit ahead of its time.
Made a little bit updates during the time, right?
We've added a couple of little bits.
That's what I mean, yeah.
The CarTrain itself has changed, but we'll have a look at the equipment that we've got here in front of us as well. That's been around for a couple of years now, the cell balancer. But apart from that, the training system has been around for a while, and we can see now that the interest has really been ramping up in the last couple of years with this system, because everyone's starting to catch up with electric vehicles, hybrid vehicles, and they're starting to see the next step, which is looking inside the battery.
This system fits perfectly to the other CarTrain as the CarTrain with the red fancy car. This is like focusing the whole high voltage system of the vehicle. And here is now we're doing a deep dive to the high voltage battery. Why it's so important to have a training system just for the high voltage battery?
There's a number of reasons, actually. So on one side, what we're doing with these CarTrains is really looking at the qualifications that you see. So there's a number of qualifications that are available for working on high voltage vehicles. So not every country has them, but there is a couple of very particular ones that you need to look out for. So for example, here in Germany, in which you find basically in a lot of other European countries as well, is the DGUV. And so that's actually the Occupational Health and Safety Organization here in Germany, and they've defined what the training requirements are for working on high voltage vehicles. And so the high voltage battery is actually the highest level of qualification that you require.
So it's more from a safety perspective in that case then?
Definitely a safety perspective, because the one thing we can't do with a high voltage high voltage battery is to make the battery safe as such. So
as you can shut down the high voltage system, but you cannot shut down the battery. That would be a flat battery then, right?
Yeah, I mean, and that is a strategy some people use and some companies use, is to set up a special tool onto the battery and discharge the battery. That helps it keep it safe. But you also have the manual service disconnect, which you can remove from the battery if the vehicle has one. Not all vehicles have them nowadays, but they might have some sort of bridge connector that at least separates the battery into two halves, which helps lower the voltage and therefore lowers the risk.
But at least there's still 200 volts then on each side when we have a 400 volt battery.
Yeah.
So also this is not a piece of cake if you get in touch with this.
And it's still high voltage as well. It is less high voltage, but it's still high voltage as far as automotive is concerned.
And when you have a completely discharged battery, I would say from my perspective now, you just have an learning objective for looking. As it's a dead objective then, right? You can't really do something with it.
That's a good point. So we're talking about here, so the name of the webinar was From the Classroom to the Workshop.
Yeah.
We're talking about how do we get the people up to the point in order to do that. So obviously, in order to diagnose correctly, and the focus here is on diagnosis. So what you mentioned before, if we had a flat battery, and you're saying, okay, let's replace this cell and this cell. Okay, you might be teaching someone the mechanical proficiency of, okay, I need to be able to do that and remove that, and to remove this cell or this modular, I need to remove this bus bar and things like that within the battery. but we want to go the step before and work out why are we replacing the cells in this battery.
And really, the hands-on process for this, right? I mean, it's like in medicine. It's one thing when you do an operation on a dead object, basically, or when you do an operation on a living object or on a live object, to stay in the wording of the high voltage battery. So, and I think what we're trying here at Lucas-Nuelle with our real experience perspective or topic, that we really create training system which are safe on the one side, which is absolutely is, as we will see in a second, but on the other hand also to be as close on the real workshop and on the real jobs as possible, right?
Yeah, exactly. So the point here is, so you just had the analogy of having someone having surgery or something like that. So we want to first of all make that diagnosis as to why we've made the decision to do the surgery, and then perform that surgery as well. Now, this is obviously, we can't compare this to a real vehicle. So, but the idea is that we're doing the same steps and procedures that you would in a real vehicle, just on a more manageable level that you can do in the classroom, for example.
Before we have a look at the system, maybe just let's start when we're talking about real cars or a real high voltage battery. We have the safety aspect, but we also have a whole lot of maintenance to do and service during the time. What about this system? So how do we get it into operation, and what about maintenance and service?
So the system here, you're talking about when you purchase the system?
Exactly. I get it now, and I want to start with it. So do I need any extra power socket, or what's the point here?
Well, it's connected to the power, of course, but it's just a simple connection that you...
So no three-phase, nothing like...
No three-phases or anything like that.
But even it's a real high-voltage system,
It's a real high-voltage battery. So you can see here lots of different cells. There's 16 different cells in here, and these are real lithium cells. So it's not a simulated battery or anything like that. We're actually looking at real cells.
So this blue cell, what we see here as a picture, is especially inside the cell.
So this one here is so I think basically the most common type of lithium cell that's ever been made is the 18650 cell. So that's the dimensions. And that's exactly the cell that we have inside of this module here. So we have a little module or a little container which the cell is inside. Now the cell is much smaller than the entire module, but the reason we do that is because we've got some circuit boards in there with some faults built in.
I see.
So we can switch faults on. There's communication with each of these cells. We can switch faults on and simulate or actually emulate different types of faults on the system.
Nice. And I think we also have a built-in charger and everything like that, so that we always can put the battery in the right condition we want to have, right?
Yeah, absolutely.
So it's nothing like with the real car that we need a wall box or anything like that to get the high voltage battery on point.
What we call the preconditioning. So we can set so if you want, as a teacher, if you want to simulate a flat battery, you can press a button, click a button, and set the battery. It will be flat. Or if you want to simulate a full battery or somewhere in between, you can just do that with a click of a button.
So you're as an instructor, from an instructor perspective, it's pretty easy to prepare the CarTrain for your lesson and so on. So you don't need a lot of preparation time. That's more like in seconds. Like, plug it into the socket, wherever you are, 230 volts or your local voltage, basically. You don't need any extra stuff here. And even when it's a high voltage battery, it is a training system, and you have created or developed it this way that you don't need an extra room or buffer zone and everything like that. What you would need, correct me if I'm wrong, when you have a real high voltage battery, right?
You have a real high voltage battery. Now, every country is a little bit different. Some don't have any rules behind it, but there's a lot of countries where if you have a high voltage battery in the classroom, it has to be secure. Basically, a lot of countries, it has to be in its own room, locked away, things like that. So we've created it in a way that's completely safe.
And I think that's the beauty here, that you have this real battery, but it's touchable.
Yeah, absolutely. So let's have a look at it in a little bit more detail. So we've been talking about its features and functions, but let's just have a look at the system. So you can see here, we've got the front end of a vehicle. And so that here is to simulate So what I'm doing now is driving the vehicle under different conditions.
That's a driving situation.
So you can kind of look at this where we can see it's like going up and over a hill. So, and we can see here, this is kind of like driving uphill where you need lots of load to get up.
So that would be the one. You have 5 different driving modes. That would be the one, okay?
Exactly.
So that's the full load or the highest load on the high voltage battery?
Number 2 is a little bit less load. Number 3 is basically even load where we're not using much power at all. And then going down is different types of regeneration. And so we can see that here. If I switch between the different modes, not sure how well that comes up on the screen, but we're switching. We can see the energy flow in this case.
So there's a movement in the LED light there, right?
Yes, exactly. Yeah. The movement is going back into the battery in this case for regeneration. And when we're using power, you can visualize seeing it coming back in the other direction here from the battery. I think blue is a little bit easier to see on the screen there.
And I think, as you say, you see the things directly also in the tester, right? That we can see the energy flow going in and out.
Can see energy flow. We'll have a look at that in a minute. So let's just have a look around on the system. So we can see up here our dashboard of the system. And that's where we're seeing, state of charge, the type of power, and we've got our ready and high voltage fault up here. Can see the other elements that we have on the screen here. So we've got a little measurement point for our interlock where we can measure the interlock voltage. We've got a number of, so we've got a high voltage fuse, which is often used by firefighters and quickly shut down the system. Not everyone's always aware of this green connector as well. This is like a low voltage service disconnect. So we know about the high voltage service disconnect in the battery we spoke about before.
Which is down here.
Yeah. But we can, yep, exactly down there. But this green one here is what we can separate basically the interlock and in some cases the power to the BMS as well. So that's a low voltage system.
So, and I think because you said low voltage, so from the eyes of the car manufacturer, this is easier to handle as you're not touching the high voltage system compared to the orange one.
Exactly.
So that would need all the PPE, where we talk later about it, and this doesn't need any PPE, right?
Exactly. Well, not necessarily, depends. So there's 2 different ways of doing that as well. So there's one with the scan tool. So we're using the tester or the scan tool, and the scan tool will take the measurements that you require to do this. So you don't need PPE to remove the connector.
That was my point. You mean for the live dead live measurement?
For the live dead, need that. So that's one point. Yeah.
And just to mention, this is not a service shutdown. This the red button here is just part of the how you say safety system of the CarTrain itself. It doesn't have a didactical purpose, right?
Exactly.
Okay.
We can see down here as well. So we've got our type 1 and type 2 with
and CCS.
CCS.
Everything is there.
Yeah, exactly. The different types. We didn't put Chardemo on there, but this is.
Are they just looking beautiful, or can you really connect then a wall box to it?
Yeah, you can connect real systems to it as well.
Yeah. By the way, we have our own. When you don't have a wall box in your institution or in your class, we also offer a wall box with the system, small one like DIN A4, like a paper page size. And this goes directly hand in hand, but like Daniel said, you can also connect any real wall box with it.
We also have our 4-channel oscilloscope, so we've got the cables connected up here. We'll have a look at some measurements shortly where we can use the 4-channel oscilloscope. Fancy. The USB cable here as well, which is where I'm connected to the scan tool to my computer.
So that means if you, in another case, then you would need a voltmeter, oscilloscope. Like you said, 4-channel oscilloscopes, also a bit of a price. Everything's integrated in here. So you could use the real, when you have some at the school, you could use the real instruments, but we have the so-called virtual instruments. So when
we'll have a look at those. We'll see exactly what that is shortly.
So we can't forget about any measuring instruments. They're all there.
Everything is there included. Now, if we have a look at the high voltage battery itself as well, so it looks like it looks quite busy here. So Leon's just zoomed in a little bit for us here, but we can see here there's the the circuit diagram of the system as well is printed directly onto the system. So if we have a look down here, you can't see it from the side, but there's temperature sensors down each side because we've got 8 temperature sensors on both sides of the training system. And you can see here, so it looks a little bit like a spider's web coming up to the battery management system here. But these are all of the various voltage sensing wires that we have for each of the various cells. And that might be a good time for us to have a look at what that actually means. So we can see up here we have BMS 2, BMS 0, and BMS number 1. And what you often have here is the way a battery is made up. You have here individual cells, but then each side, more of those cells are packed together into a module. And on this system, we have 2 modules and we have 2 BMSs. So we have 1 BMS for one module, second BMS for the second module, and then we have this BMS 0 is overlooking both of those modules and sort of controlling everything that's going on within the battery.
And they are all communicating with CAN high speed, right? That's
exactly.
Also there.
Yep.
Okay.
And then just to finish up here, I mean, we've got the 12-volt battery that you can see up here with our classical 30, 15, and 31 terminals. But we also have here our high voltage negative relay, our high voltage output. So this is what would then go onto the inverter to drive the motor.
And there you would do the live dead light, also the dead measurement basically.
Exactly, yeah. And then we've got our pre-charge resistor for pre-charge relay for soft starting of the system, and then our main plus relay here as well. So this is the measurement we'll have a look at shortly.
Cool.
But I think what we might do is just have a look at the whole system, what's going on. So I've got it regenerating right now. So I think it's a good time to have a look because we're at a very special condition right now of cell balancing. So we're going to have a look at cell balancing, and then we'll go straight into a fault that we can look at first.
Okay, cool. So this is now basically what we see now is the learning environment. And in this learning environment, you don't just have the whole of the theory basically explained in theory, animations, videos, experiments, and their knowledge test. But we have also the virtual instruments, and what you show here is now the diagnosis system, like a real diagnosis system, especially developed for the battery management system of the CarTrain, right?
Exactly. So we decided against having an OBD system. So a lot of people are expecting to see an OBD where you can connect in your Bosch, your Snap-on, your whatever it is, Autel, and we decided against that and built our own system so that anyone can connect up to the system and do it. So
and that you have also the same conditions referred to theory, because when I have a Bosch or a Sun or whatsoever, or Snap-on,
some are better than the others and can't
we don't know which values they offer, right?
Exactly.
Yeah.
So we decided it was better for our customers if we just produced it ourselves. So
it looks like a Christmas market here. Everything is blinking.
Exactly.
What does this mean?
This is the cell monitoring system. So right now you can see all of those blinking lights, and this will change if I change the system here. You can see how now it drops down to
okay. Now we see loaded is, and we take now
current
energy out of the battery, right? Electric energy.
So you can see that there. So and what we're actually looking at now, it's because I just took it a little bit. So the upper voltage of a lithium cell is 4.15 volts. So as soon as it gets above that, it becomes dangerous to the cell. So the cell can be quickly damaged. So what the system is doing there is balancing it. It's bypassing the cell. We'll have a look at an animation in a second. I just wanted to make sure everyone's seen this. We can see each of these blinking LEDs here, which means it's bypassing. So we see none of these cells are going up to 4.16. They're all being held at that 1.15.
Okay,
4.15.
and the aim is, obviously it takes a while, but in the end the system will calibrate all the cells on one and the same voltage, right? Exactly.
So it's going to make sure that they're all at that 1.15.
Okay.
So this is, we'll have a look at this animation, what that actually means, but this is what a lot of manufacturers, when they recommend to leave the low or the smaller type of charger, so not always do fast charging, because fast charging doesn't do this balancing. Fast charging really only goes up to, say, 80%. We can see here the current, if I was only at 80% state of charge or 70% state of charge, that current would be much higher. Yeah. So it slows down at the end there to make sure that you're not overcharging these the cells there. So, but let's just take a quick look at what this looks like in balancing. So if we have a look at how to charge different types of cells. So right now we have
that's the series connection of the cells, what we've seen here on the drawing as well, right?
Exactly. So if each of these cells only have 4.15 volts, we need to put them in series to get up to our 400 volts or 800 volts or whatever it is. So we need to make sure they're in series. But when they're in series, if you want to charge them, you have to charge them also in series.
Of course.
That amount of amps that's going through is going through each of these at the same time. And the problem is with the cells, as they degrade over time, they have what's called an internal resistance. And so we can see the effect of that here. Or if you didn't balance, or if the cells are not being balanced, they can get further and further out of range.
Because they discharge and charge not all under the same conditions.
Exactly.
It's not like that you can say, okay, even when we put in the same cells, it's not like after 1 year that they are all on the same level.
Exactly.
That's when we're talking of state of health then, right?
Correct.
Okay.
Exactly. So we'll just have a look. So as we began to charge the cells, we can see the one on the left here is at a much higher level already. And the problem is the other two, they need to continue to be charged right now in order to get fully charged. And so, but this one here now, the voltage would continue to rise and rise.
Then we will kill this cell basically.
We'll either kill the cell or there's a danger of causing a thermal runaway.
Okay. That means when basically it's like, it starts burning, right?
Exactly. I think we can all agree that's a bad thing.
Yeah.
So, but let's have a look at what this balancing actually looks like now.
So what we see now, it's just an example. This is not the way it is in the car.
That's not the way it is in the car.
Okay.
Or some little batteries, in the vacuum cleaners or bikes.
Okay. You don't drive with them.
But before I showed all of those wires, what I mentioned looks like a spider's web down the side of the system, are actually these. So we can see here, this is the circuit diagram for a relay, a resistor, and here we have a switch. So the switch in this case would of course be a transistor or so. But these wires, this serves two purposes. There's also a voltmeter on this side within the BMS which can measure the voltage of this cell. So it serves two purposes. It's the balancing module and the voltage sensing. But when it determines that the voltage has been achieved, this is the bypass that's occurring within the system. And so we can see here, that's what those LEDs, the LEDs when they are blinking is showing what happens during this this closing of the resistor.
That means the blinking means the closing of the transistor. So so when a cell is blinking, it's bypassed.
Correct.
Okay.
Yeah, exactly. So we'll have a look and we can see that example right there. That's exactly what's going on within this battery right now. So it's at the absolute limit. And this is a great thing for the battery to do. So you can see here, there's still one that hasn't quite ready. It's not blinking. Now they're all there. Yeah. So, this is really good for the battery to be balanced regularly like this. And I don't just mean this battery in the CarTrain, I mean in your car. It's a great thing to let the charger continue on and let the vehicle completely balance out.
So that means if you just do the fast charging and not the normal charging with the balancing process, that obviously your high voltage battery will die earlier. Or not maybe die, but cause problems or reduced mile range at least.
Exactly. So through that internal high resistance. So if we have a look, so let's gives us a good lead into what happens. So when cells die or get
used,
as they get used, as they deteriorate over time, what actually happens to them?
Yeah, I mean, you can't avoid this, right? This happens when you drive, when you use an electric vehicle. So that means we're going now from the state over. I think it was always already impressive to see what we can do on this high voltage battery in a good condition. But now we go over into the diagnostic case, in the maintenance and diagnosis part, as we can activate a couple of faults, high voltage faults inside the high voltage battery, right?
Exactly. So we'll have a look here inside of the tester. So this is now something that you don't have on real testers, is a administration function, and we can go here to set the faults that are within the system. So this is just giving you an overview of some of the faults that we can connect into it. There's also, these faults are available within the LabSoft as a customer complaint.
When you just shortly scroll down.
Yeah, I'll show you that in a second. I just wanted to show this here while we're here. So we can show here different types of temperature faults, interlock faults, and then we get into some interesting with the relay faults that we see here.
Welded shut and everything.
Welded
like
shut,
that, right?
or completely open.
Classic one I see, loss of isolation.
Yep, exactly. CAN bus.
Active discharge. That sounds a little bit fancy, more special.
Yep. So we'll look at that with the oscilloscope. So some of these is where you begin to have to use the oscilloscope to understand it. Or we can go down here to each of the cells. So cell 16, and we can put in here open circuit or high resistance faults into any of these cells as well. So that's just available.
And what I just see here, I think what's interesting that you can also attack the field of temperature problems, which can be, or which I think is a very interesting one, as it can be electrical problem, so that you don't have a real temperature problem inside the battery, just an electric one, which I find very interesting to understand, because like when you have the situation, a car comes in the evening hours, and you have to decide either to put it in the workshop or not. So there's the question, when there is in the fault code memory, for example, a problem with the temperature, you have to decide where you put the car. And when you can say, okay, wait, this is just a temperature problem, but more on an electric base because one of the sensors is broken, the battery has all the temperature sensors, like a real sensors integrated. Or if we really have a temperature problem that the battery heats up, then we shouldn't put it in the workshop. Air thermal runaway, and when the battery catches fire, then the car catches fire. When the car catches fire, the building catches fire, and that's
and all the other customer cars.
And all the
So
this decision can save your job life.
Yeah,
basically,
absolutely.
Right?
So it's a good point. So we're just having a look here at what those temperature sensors are. There is actual temperature sensors in there, and you can actually replace these with So these are NTC temperature sensors, so they're real sensors, and we have different values. So we can put them in there and actually have different values to help students understand this problematic. But what we also have here, what I can just quickly, I can open circuit one of these, and we can see the result on the scan tool here itself. So right now, as I mentioned, NTC, when they're open circuit, they show very cold temperatures. It's interpreted as a cold temperature within the scan tool.
This is now great to see when you have this experience where you can directly say, hey, of course, the one cell is not in Alaska or somewhere placed. It's obviously electric fault. And it's like you said, it's an open
circuit.
Open circuit, yeah, exactly. And this is where I think through your experience where you can easily do a diagnosis then, right?
Exactly. So we can see that, or if I short circuit the cell.
Now it's getting interesting.
Now we can see how it warms up, and now this is where you might see exactly the situation you mentioned before. There's a red triangle on the car saying a battery temperature fault, and you might be, oh my God.
Exactly. So we see here the high voltage fault comes up, and the cooling directly
the cooling
starts,
is
right?
on the whole time, and so you get the car and you're like, well, should I really drive that into the workshop right now? maybe not the best idea. Let's park it outside, and this is where you connect up your scan tool, and you can see this here and see, okay, one range. So it's not that every cell has its own temperature sensor. They're usually spread out, and one of them is at 120 here. But let's just have a look at this this diagram in the background here. So as you mentioned, this is either critical fault or non-critical fault. And so you can see here, this is meant to show the distribution of heat within a battery. So if we had one point that was at 120 degrees right now, or if it's at 60 or something higher than normal,
yeah,
and the cells next to it are also pretty hot, and the one next to that is also pretty hot, that's pretty important to see. Whereas the temperature fault that we have right now is one sensor that is
and all the others are good, right?
And the others are completely fine. That's most likely going to be a non-critical fault.
So which doesn't make sense, as heating doesn't just cuts off at borders where you say, okay, to here it's hot, and after it it's not hot anymore. So that doesn't make sense, right?
Yeah, exactly. So that's what it looks like as a non-critical fault. But just a very important thing to do, exactly as you mentioned.
And the beauty here is how easy you show this to us. When I imagine this on a real car, what I need to do to show that to the students, that will take a whole day maybe, hey?
And the question is, do you want to put faults inside of a real high voltage battery?
That's yes, yeah.
So in here we can see all of the different faults that have come up as well.
Ah, with the real fault codes, I see it here.
Yeah,
P1,
so
cool.
real fault codes. So what we're going to do is delete those right now, so we can go back as, you know, good practice. We can see, okay, everything's fine again.
Looks good.
And what we're going to do now is we're going to have a look. So all of these different types of faults, as soon as I click onto these, it's going to cause a fault within the system.
Automatically.
Automatically. So, and I might just click on this one down here, 21, reduced range. So
that sounds interesting.
Now,
I've heard the click, okay.
Yeah, you probably didn't hear that on the system, but let's just come over to the system now, and we'll take that.
So the car came into the workshop now?
Yeah, exactly. The first thing you're going to do as a technician is take the system for a drive and confirm the customer complaint. So I've deleted all the fault codes before, because that's a bit of a trap. Sometimes you get a vehicle comes in and you just read the codes, and what we see, especially with younger technicians.
Or you start here with the workshop order where it said like, hey guys, the customer complained, and go for it, basically.
Yeah, exactly. So, and then you read the fault codes, and there's like, woo, all these different faults in there, and you're like, where do I start? What am I looking at? So, and that's, it can send you off on the wrong track sometimes, because cars often have lots of faults within them, lots of DTCs. So you can record them down, but then delete them, and then start again.
See what the actual condition is right now.
Exactly.
Right?
So we've taken the vehicle for a drive. In this case, the high voltage light, fault light has come up. You can say, okay, what's going on there?
We see also that the cooling is on.
The cooling is on from the start, which is also perhaps a little bit strange. And okay, so unsure, take it for a drive. And now I'm going to come back again to my scan tool over here, and I might just read those codes again. So have a look over here, and we can see here, cell error, okay. One of one, so we've got a voltage low.
Okay, but we do not know which cell right now, right?
We don't know which cell,
okay.
Exactly. So what we might do then is come over to our,
and the interesting thing was it said sporadically, right? So that means for us as a technician, oh, it doesn't appear all the time.
Intermittent, exactly.
Yeah.
So, sorry. So if we have a look at the various voltages here, so this is interesting. So we're going to just skip forward a little bit. So I'm going to tell you right now what we've done is added a high resistance to one of those cells. So a high resistance to a battery cell is going to cause that cell to function abnormally.
Like what we've seen with the balancing and everything like that, when the system, when the resistance gets higher, we have a lower state of health, and the cell output is not the original output anymore.
Exactly, that's exactly what's going on there. So now we've seen this before about one of the cells is at a low voltage here. So, okay, we can see the slot 6 is a little bit low, but it's 0.03 or 4 of a volt. That's not too much.
From my perspective, I would say right now under this non-load condition, it looks not too obvious to me.
Exactly. And so that's where we get to, so good old Ohm's law, where we're seeing that it's a battery cell. So
yeah.
it's hard to, well, it's impossible to measure the resistance of a cell. So we actually have to calculate the resistance of a battery cell. So you just mentioned there before, not under load, but now if I put the system under load, we can then begin to see some interesting things. If I go into regeneration mode, you'll see something also very interesting. How, okay, it's at I think we just seen slot number 3. We can see that's already at its higher limits.
Oh, yeah.
Or if we put it under load, because we're at almost 100%, it didn't have much current, but we can see by driving under high load, we've got 4 amps of current, and we can see here we've got a much higher voltage drop across cell number 3. So, and that's what I mean before about it being interesting, and what you also said before as well. When the system is at idle, we can see here, you can't tell the difference.
True.
And so that's also showing, okay, you need to do some of this homework before you pull the battery out, because a lot of people still think they can pull the battery out. The cell voltage was low. That's what the scan tool said. And they think they can just measure across each of the cells and say, okay, that one's low.
And it doesn't help you.
But it doesn't help you.
Yeah.
You need to put the system under load to start with.
Okay, but we've seen now slot 3 is the bad guy, right?
Is the bad guy. And so what we're going to do now is actually show this as a swap. We're going to actually swap this battery cell out, number 3.
But okay, it's like with my remote control. One of the cells is broken. I just get a new one, and don't get the cell from the supermarket maybe. But what about why we're not starting directly changing it?
Yeah, so we need to get a separate cell now in order to do that. So as you mentioned, we need to find out either a cell. Reality is you might need to buy a complete module. So it's getting less and less on the cell level to do that. It's more likely going to be a module.
A module is a bunch of cells.
Yes, exactly. Okay. So what we've seen before, cells connected in series, series or parallel, build up to a module. But what we have here, this is a spare cell now. So this is the system that's relatively new here. It's been around for a couple of years now, but active cell balance it with test function. So this here is, we can see here, we've got a separate cell, and we're going to build this one into the CarTrain now. So this is what you do also in the workshop, but you're talking about something much bigger than, it's going to fit onto this whole table as opposed to this tiny little cell.
Well, it's amazing because that's pretty lightweight, so easy to handle in class.
Exactly, and it's going to fit for the CarTrain if you buy one of these. So the picture on here is actually a photo of a real one, or an animation of a real one. They might cost $5,000, euros, or whatever it is. And then they're only going to fit certain vehicles as well, maybe a type of vehicle. But this one here, we've got this here. Now, I hope you can read that. It's telling us here cell voltage is 9.93.
Leon prepared everything that's readable.
Very good. So 3.93. We've seen on our scan tool before the voltages were about 4.03. So we can see here we need to balance this one up a little bit further. So because we need to get this one at the exact same voltages as all of the other cells that we've seen before as well.
Which would be 4.04 or 5?
4.04, so let's just do that. And I've set the voltage now to 4.04. I'm going to press yes. And we can see now that this has now got an LED that's blinking away. And what that's doing is charging the cell up. So at this stage, the voltage is higher than what the target voltage is higher than the actual voltage that we have. So it's going to charge that up. And what it's doing is charging it, and then every now and then it's going to discharge it, like just to get rid of surface charge on the cell.
Okay.
And it's always checking to make sure, and that will go down to this second decimal point of our voltages. If the voltage is too high, it will actually discharge it as well.
Okay.
So it will set the exact voltage that you want.
But I'm now in a hurry. The customer said like, oh, I need to pick up my car right now. What happens when I've just built in the new cell as well?
Well, what we've seen before, how did the vehicle know that that one of these cells was faulty?
Because of the voltage breakdown.
The voltage difference. So before we've seen a voltage difference of, what was it, 3.77? One was at 3.44 roughly. So about 30, so 0.3, 0.2 volts difference. So as soon as there's that large difference between the cells within a battery.
It would still a problem. Also the BMS would say, are you crazy? What's wrong with this cell? So even when we know it's a new cell, the car doesn't necessarily know it's a new cell, right?
Exactly, it just knows there's a problem.
Okay.
And so if we put that in at such a large difference, you have to do that balancing for much, much longer. So we've seen before how slow the current went down to 0.7 amps or something like that. All the others are blinking and balancing, but the poor cell that you've just added needs a lot more. And it's
okay, that would be out of...
So it could take a long time to balance it if you just put it in. And the BMS, the car is going to be complaining the whole time, saying something's wrong. So the best practice is to balance it up to that same voltage that we see there before.
And the best practice is to do it at the first step before you work on the actual car, because the balancing process, like in the real car, also takes quite a few time, right?
Could take a long time. This one is actually going a little bit quicker because we prepared it. But in the real vehicle, this could take hours. So it could take half a day to balance up to the same level as all the others.
So it would be not a smart idea when I take out the whole battery maybe, which also takes time, and then I start the balancing process.
Exactly.
The other way around, in the best case, when I'm pulled out the high voltage battery and I'm ready to put it in, it's more or less ready.
Well, you also have to know what the voltages are before you pull the battery out.
True, yeah.
So that's also the case. You have to work out what is the average voltage.
Okay, yeah, for sure. Yeah,
I mean, there is some tools that allow you to connect up to a removed battery, but that's some pretty high level stuff. So we're talking about, if you've just got normal stuff in your workshop, you want to be able to read all those voltages.
That makes sense. And guessing is not an option, right?
Okay, so that's balancing away. Let's have a look at our system here, how we would actually go about that. So first of all, let's just take a look at some of the PPE that we have here. Now, this might be new for some of you, but when we start working inside the high voltage battery, it's actually important now to have face protection. So in this case, a helmet. The reason for that is because we're working on
live conditions.
On live conditions. So the battery, as we said before, is always live. It's not like if you're replacing an air conditioning compressor, you can shut down the vehicle. That part of the system is safe. You can remove that. That's completely fine. But when you're working on the high voltage battery, there is potential there for live high voltage. So we've seen it before on certain videos.
Yeah.
If you pull apart a connector that has current flowing through it, you're going to cause a arc flash or some sort of arc blast, arc flash, where you're creating a ionization of the electricity. Problem with that is if that happens, if you're working on the battery and you pull it apart and that flashes up, you might get the flash in the eyes, of course, but the big problem is that you go and you can breathe in that flame. It happens, unfortunately, quite a lot with electricians. Not a lot with but it does happen. There's potential for that to happen, and they get burnt from the inside, and you burn your lungs from the inside.
Yeah, that doesn't sound good.
That's why you need a helmet like this, especially with a neck protection. We obviously also have our gloves here as well. So interesting, there's different types of gloves available where you are around the world. So this is typical for the European type of gloves. They're longer, a little bit thicker. And then for the US, we have these gloves, which are a little bit shorter. These are like linesman's gloves.
Yeah.
They're a little bit thinner rubber, but you have a leather overglove to put on top of that.
So
put on top, not underneath.
we had that at Skills USA. So, but don't worry, it doesn't matter where you are. When you order the system, we will make sure that you get the right PPE for it, which fits to your country.
So I'm not going to go into detail about the PPE. We've got plenty of other videos about that, but thing is to make sure they're tested, class 0, 1000 volts, checked regularly and things like that. So, but going to just check them here. This is the called the field test. So capture a lot of air in there and just make sure there's no leaks. Cool little tip is that we found from our mate Bound. He told me this just recently. I always used to fold them up the flat edge and you don't capture much air. If you actually pull it out to the side and then do it, you capture a lot more air.
That's a big difference, right?
Huge difference. So you can see that, and I'm putting up to my ear to make sure I can hear that, so in case there's anything. There's that. We need measuring devices as well. So this one here is called a Deuce-Pol. It's a type of, well, that's a brand name. This is essentially a voltage tester. Now the beauty of this thing here is there's no cables for me to remove. So the problem we have with the multimeter is there's a potential that you can cross the cables up for current measurement. So on the multimeter you can switch it around, measure voltage, or I can measure current. And the difference between those two measurements is one is parallel, voltage is done parallel, current is done in series.
Yes.
So we have the same problem we had before with our arc flash is if you measure all of a sudden current and across 400 volts, the multimeter might blow up as well.
Okay, I see. Yeah.
Or cause damage to something. So
absolutely, yeah.
It's highly recommended to use a system like this. You can't measure it, you can't mess it up. You can't measure it. It is always measuring in parallel. But you can, of course, use a multimeter. It's not absolutely forbidden. Here in Germany, you have to use this. They're saying use this. But in a lot of other countries, my experience is most people don't know about that. So it's a little bit just letting you know that there is other devices out there to do these measurements. A couple other little bits and pieces we have here working on the live system. So we've got the insulated tools because it's the battery. If you were to isolate the system and then work on the inverter, you don't need insulated tools because
cut it from the high voltage battery, the rest?
Exactly, we know it's not on high voltage. Another thing that we have here is our lockout padlock. So it's a little plastic padlock. It's not a high security padlock. It's not intended to be high security. It's meant to be seen. We'll have a look at why that is. So we also have this here.
Lockout box.
Lockout box. So the way these work, so for example here, you can put the service plug or ignition key, things like that into a system like this and remove the key. I put that key in my pocket and no one can open this and no one can start the car. So that's the point. And the reason it's got lots of holes around here is so that everyone who's involved with the situation puts their lock on there and no one can start until everyone
or in a class situation, always the instructor can additionally save the box and said, okay, show it to me, and first, or just when you show to me everything, then I open my lock.
Exactly.
You can go on.
We actually had experience with this in the mines, worked in the mines in Australia, and that was when you're walking inside of like the machines are so big you're walking inside of them and they have boxes like that on the doors or on the start so that everyone inside.
We talk about another security level, right?
Yeah, but it's the same thing. So it's in the end it's about keeping people safe. And so I know in Australia, at least if someone cut this off and said, look, I just need to start it, and they cut this off, you basically go to jail. So that's how serious it is. Like I said, it's not about being mega secure with the padlock itself. You could probably break it. It's with with a screwdriver.
Yeah, but normal human sense should tell you like, okay, I can't touch it.
Yeah, the problem, of course, with vehicles, you might have someone in the dealership or at the garage that say, oh, I just quickly need the kilometers of the vehicle to write on the repair order or something like that. And they come out and they just press start, and you're working in the back of the car, and all of a sudden the car becomes active. And it's like, that's the sort of situation we're trying to avoid here.
And we have pretty small cars here in Germany, but even when we look to other countries, they have pretty often bigger cars where you maybe don't see that someone is working.
What if you're in a bus or a truck or something like that? So
yeah.
Completely, or under the vehicle or something like that. So there's, it's better to just get rid of all the risk and make sure that you can't do it.
Yeah.
That's what we're trying to avoid here. And this is what, we're practicing here so that when students eventually become technicians and end up in the classroom, they're already doing the best practice. They're already doing the right things, job ready before they get there.
But you just dropped off interesting one. So while Dan is preparing that, so he's just said trucks and so on. There is also CarTrain version, which is then called the truck version. Oh, the balancing is ready for commercial vehicles. So when you come from a field of commercial vehicles, then there is a special version with a special course just for the field of commercial vehicles.
Correct. So if we have a look now at our balancer, you might have heard it. It's sometimes Teams doesn't allow all the sounds to come through, but we can see here now that the cell now balanced to 4.04 volts. Remove the cover and the cell. We'll have a look at that in a second, but that's what's going on right here. So that is now ready. We've just been talking too much as usual.
Yeah, but now it's balanced.
Now it's balanced. So what we're going to do is do the preparation work to get inside the battery.
So as I understand you correctly, we can do the tester-based shutdown, but today you want to show the manual shutdown with the live dead live measurement.
Exactly.
Okay.
So live dead live measurement is making sure, essentially what you need to do is you need to verify the system is shut down. Absolutely 100% make sure that the system is shut down and it's safe to work on. Because what can happen is we have these relays, if they're welded shut, which has happened, doesn't happen very often, but if it does happen, you might be working on the system, but it's not actually shut down.
Okay,
so the main contactors, there's different manufacturers, different countries call them different things. System main relays is the Toyota term. Contactors are used for different ones. Contactors are just large relays. So essentially the relays that connect the battery to the rest of the vehicle. We're going to check that. We're going to do a live dead live. You can do it with a scan tool where the scan tool is taking the measurements for you, but we want to actually see what's going on, so we're going to do it manually.
Let's do it.
So first thing we're going to do is I've switched the system off. You'd put the key inside of the lockbox, so do that. But on this system here, we're going to remove this green connector here as well. So what I can do is just pull that out, and we can see there's 4 cables here. This is a part of our interlock. And in this situation, it's actually the BMS for the power supply for the BMS as well. But this little connector has a nice little hole in it that allows you to put the same padlock in there, and we can't put that back in there now. So again, we're securing it against someone coming up and starting the system. That's the point of this step. So, and I've put that key directly in my pocket. So this is my responsibility, my life that we're talking about. Yeah. I'm going to be working on the car. I'm responsible for this key. There's no point doing that and then just leaving the key next to it as well.
I'll just leave it at the lock.
Leave it in the lock, yeah. Great idea.
Just another question, because I noticed from former days, what about disconnecting the 12-volt battery? Would that also be...
You see it less and less now.
Okay.
That was one of the things we used to do back in the day, is to disconnect the battery, because our relays are being controlled by our 12-volt battery. But because we've just done this step, this is a little bit, we can...
But if somebody would like to do that, you can just pull it out, basically.
You can do that.
Yeah, okay.
Yeah, that essentially does the same as what we've done there. But it's less of a problem nowadays.
Okay.
In the old days, you disconnect batteries and all of a sudden the radio doesn't work anymore and this and that. So, but...
I see.
So, now what I'm going to do is roughly show how this voltage tester works.
Yeah, I
Now,
will say what it shows.
you mentioned before, yeah, it's a bit hard because you have to have the camera from above, which we don't have right here. But essentially this has, so it's got 2 points. We can see here lots of little LEDs that go from 12 volts, 24, 50, 120, 230, 400, 690. And these are the lights that whatever voltage is being measured across here is going to go up to that point there. So we'll have a look at that in a second. And it also does like resistance checks as well. But if I just put that into the 12-volt battery for now to start with.
12.
So the first LED is shining up here at 12
exactly.
volts.
So that's the live measurement.
So that's the live measurement.
Which is important to do at DC as the dead measurement is at the DC source,
exactly.
Right?
So what I just did is made sure that this works.
Yeah.
So there's no point coming along and going to our high voltage point and this is broken.
True.
If you come up and go, oh, there's no voltage there. And then, okay, we start working on it and get zapped. And what you mentioned, so a lot of people go up to a power point and they stick this in because there's electricians use this to measure voltage at the power point or other points. The difference, what you just mentioned, is that's AC, so sine wave. We need to measure DC because our battery is DC. So there is a possibility if you measure it with AC that you're measuring the wrong thing. And it might still not, you're not proving that this is actually working. So you just hold that for a second for me, please.
Yes.
I'm going to get prepared here with my face protection. Because we're about to...
And I think here's the interesting thing now. When we are working on a normal high voltage system, after we've shut it down, we can take out the PPE. Here, we need to keep it on, right?
It's really bad to talk with me right now. So let me just take this measurement. We can have it the next discussion. So we've got our high voltage point coming out of the battery here. And I'm touching the contacts.
It doesn't say anything.
So nothing.
Nothing, yeah.
But I can't see anything. We don't know if I just killed the meter again.
Okay, so now you did the dead measurement and now you're going back to the live measurement and it says still 12 volt. So the voltage checker is still working.
The voltage checker is still working. So we've now verified that the system is safe. But as you mentioned, we still have to use our PPE because I'm going to work the battery. So I'm going to start removing that cell from the battery. And maybe you can explain what's going on because I don't think anyone can hear me when I've got this on.
I do my best. Or you can just do it blind with the things open. So, okay, in the first step now, we have to disassemble the cover, right? So basically, the cover is also part of the interlock. So when you would open the screws, or the students would open the screws, while the system is not shut down, or while the system is live, this will cause an interlock fault, which you also can measure at the interlock testing points. So Daniel now did it quite a few times, so it goes fast. I take over the cover, and this is also where you see here basically you see the connection for the interlock, and as soon as this is lifted and the electric connection is interrupted, then we get an interlock fault.
So I'll just explain this.
Yeah.
So obviously the system is completely safe. So we're not, I've taken my helmet off just here for a second just so you can hear me. But the system, we're not wearing the protective equipment because we can get hurt on this. We're wearing the protective equipment to make sure that the students are going through the right process.
Exactly. And this is the challenge thing here. Working with those things is much more challenging than doing the work without it, right? So you have to train this as well.
Exactly. So there might be some frustration in the workship to just get rid of it. And it's easier if I don't do that, but we're trying to avoid that. We have to avoid that. So by the way, this is our temperature sensors that we mentioned before on the side there. Now, if we have a look down here, these are the covers that are covering the contactors. I'll just remove this here, and we can see down here, this would be our bus bar connecting these up in series. So we can see the cell has a positive and a negative, and how they're connected together and causing that series connection to increase the voltage. So I'll take that cell out now. We'll have a look at that.
About what cell did we 3, right?
3.
3, okay.
I hope.
So like we said, the balancing process is ready. So this is now absolutely perfect from the timing. That means we can directly swap the cells. So I'm not allowed to touch anything here. So, okay. So the broken cell.
Now I don't need my gloves in this case because this is not only at 4 volts.
Of course, yeah. 1 cell is not dangerous, 20 cells are. Okay, nice. So, yeah. This cell goes in, and now you have to assemble everything again. So we should have like time stop, Leon. We should install like a time stopping feature that we can see if Daniel's getting faster over the time.
Keep the workshop, the area
clean and
nice
safe.
and clean.
Yeah, of course, yes.
It's not good to have the tools might accidentally get left inside the battery.
So very nice. Cell is installed.
Thank you.
I say it's tricky. It's tricky with the gloves, but it needs to be done. And even in the US, then you have on this one even the leather gloves on top of it. So
exactly.
This definitely needs training. We've seen that at Skills USA when the students were under time pressure, that it really cost them some time when they were nervous, and then they had to deal with this 2-layer of gloves. That was pretty interesting to see.
Yeah.
Don't get nervous too. It's all good.
Yeah, and that's the point about we're trying to get people to have some experience before they start working on the vehicles.
Absolutely, in a safe environment.
In a safe environment, because let's face it, pressure is there in the real life. So it's better to make mistakes here than
for sure
on a customer's vehicle. So that battery is now put back together. I can remove my gloves. I'm not going to be touching the high voltage at all anymore.
So we remember we had the problem of reduced mile range and we had the high voltage fault. So basically, that's now also tricky to get this guy back.
Exactly. So we've got this special tool here that allows us to clip in. There's a special little connection under here. If you don't do that, the system won't go back together. You need a special little thing to go inside of here, and then it goes back together quite easily. So right now, in principle, our system is now ready
for test drive.
For a test drive. So first thing, put the ignition on, go into ready mode, and we'll take the vehicle for a drive.
Okay, we don't have a high voltage fault on now. Let's see what happens.
So come back over to our scan tool here.
Slot 3 was the guy.
Slot 3, we can see we're now at the high load. And basically, that system, so if we just turn that off. Okay, so there's a little bit,
yeah.
It's because I just put it under load straight away, it removed a little bit of the surface discharge, but it doesn't have that huge difference that it had before. That's going to balance much easier than if we didn't do that as we had before.
And as we see, even under load, the system accepts it.
Yeah, absolutely. So,
okay, cool.
Yeah, so that's the cell balance that we've just done.
So like you've seen, we have a couple of other systems, other diagnostic faults as well, where we won't run through now. But I think that's the most interesting and impressive one, as we need to have the cell balancer. And what you say, as more vehicles, high voltage vehicles are on the road, doesn't matter if EV or HEV or fuel cell vehicles and so on, they all have some kind of a battery maybe. But the cells will be worn out over the time. So what you've shown here is not a super special task which happens one day in a month. In the future, this can be an all-day task, right?
Yeah, absolutely.
So pretty cool.
Yeah, so that's cell balancing, what that looks like. So we mentioned before that we have a look at how those relays operate as well.
Ah, true. So this basically that we visualize the starting process of the high voltage system, right?
Exactly.
Go for it.
So we're going to use our measurement leads over here. So now you can't do these sort of measurements on real vehicles. I mean, you can if you're starting to do some funny stuff if you get this special measurement breakout boxes that you can get for some vehicles.
If you're in a Crocodile Dundee mode, basically, yeah.
Yeah, back probing and things like that. So this is where we sort of go beyond the real vehicle, where we're able to measure inside of the high voltage system. Which
makes sense, as this is a training system.
As a training system, but it's not something you would want to do on a real vehicle. So otherwise you might get a little bit, yeah, I mean, one of the things I'm worried about is instructors getting a little bit blasé or a little bit comfortable with these vehicles, and all of a sudden start putting on measurements or faults. Yeah, sloppy, confident, like overconfident.
Overconfident.
Putting faults into real vehicles. There's a lot of theories out there that the first people who are going to get hurt are instructors, because they want to show how these vehicles work and things like that.
We had examples in Germany for this. We can tell stories, yes.
Yeah, unfortunately. So we've got to be careful about this, and so that's why we've designed this. So like we said before, normally you wouldn't have these types of measurements on a real vehicle. But we're doing that so that people can understand what all of these are.
Okay, you have now connected the 4 channels, basically, one to the high voltage output and the other 3 to the different 3 relays.
Exactly, so that's our high voltage output here. So we've got negative and positive directly into the high voltage system. And then we've got our channel A is on the negative pre-charge, on the negative relay, not pre-charge, negative relay, on the positive pre-charge on this side, and then the positive main relay on this side.
And obviously disconnected to vehicle chassis, as we hear in the 12 volt system, right?
Exactly, so high voltage system, its own network. So we've measured that there, and then we've got the 12 volts on the control of the relays.
So now we need the oscilloscope, right?
Exactly, so let me just go back out of here. We'll get rid of that fault. I need to go here, reset faults before we start doing other things. All faults are turned off. So let me have a look up here. So relays, high voltage system relays. So just to have a quick look at what we're looking at here. This is the relays within a system. You can see how they close. This is our high voltage battery here. And when those relays, so pre-charge switches on here, and this is pre-charging the capacitors. You've got massive capacitors inside your inverter. If you just connected without this resistor, so we can see this is our pre-charge resistor right here. We're bypassing it through that resistor to slowly charge those capacitors. There's capacitors right here. If they were without that resistor, they would act as a short circuit. You'd basically melt all your cables. Yeah. So this is what we're going to measure right now, is this pre-charge phase that we see here.
I mean, that's basic of electric fundamentals, right? Where you see when you build up the circuit, where you charge a capacitor over a resistor, which gives this typical curve on the oscilloscope.
Exactly. We'll have a look at, just because we're going to see it in the same section here, the system, when we shut it down here, so as the system discharges, it's discharging into the 12 volt battery. So you have to The
Smart.
capacitors,
Yeah, of course, yeah.
you have to charge capacitors, they have to discharge the capacitors as well.
So this is active discharge,
This
right?
is active discharge. There's something called passive discharge, which is using a resistor to basically waste that
Not
energy.
so smart, exactly,
heat.
and this is much smarter.
It takes a long time on one side, but it also wastes that energy. This here is throwing that energy back into the 12-volt system via the DC-DC converter, so that it makes the system safe as possible.
Cool.
Okay, so let's have a look at the oscilloscope. So double click, make that twice the size. So we want to set that to about 1 second to start with.
Then we switch to 4-channel mode.
Exactly. So we had here channel A was our high voltage. So
why Daniel is setting this up, I think the beauty here is as well from the oscilloscope what we see, that this is a real oscilloscope. It is in a virtual environment, but the students have to do exactly the same settings like they would do on a real world oscilloscope basically. And the good thing here is we don't have an auto set button. That means the students have to understand what they want to measure and do the adjustments beforehand, and there is no button where they just can skip that and where the oscilloscope is doing the job for them. All right, then you measured something.
So what I did then is just put the system into ready mode and then switched it off almost straight away. So it was only on for 3 seconds or so. And so we've got 4 channels here. Now what I'm going to do is, you can see they're probably a little bit confusing right now because
looks a little bit like modern art. Yes.
There's too much going on here. So channel B was our negative relay, and that's the one that's been on for the most of the time here. So I'm going to just shift that down to help kind of see what we're looking at. So this doesn't change the voltage or anything. That voltage is exactly the same. It's just moving it down so we can sort of separate it from the others. But what we can see here, this is our negative relay was switched on at this point right here. And the blue one, this is the, let me just flash that on, off, so you can see which one I'm talking about. This is our high voltage here. This is at 20 volts per division. Division is the lines that we see here. So 20, 40, 60,
about
just
60.
over 55, 65 or something like that.
Yeah, so we're in the high voltage area, clearly.
Yes, the other ones here were only 5 volts per division. So on the same scope, different voltage levels, but they're all within that same range. So this one here is, so yeah,
something
12 volts, thereabouts. So what's happening here though is the negative came on, and then we have this light blue one here in the background. Let me just flash that one so you can see.
Which is obviously the pre-charge relay, right?
This is our pre-charge relay, exactly. So, and we can see that those two correspond with this build-up of the voltage here, and that's that slow build-up of voltage that we spoke about before.
Because of the resistor at the pre-charge relay.
Exactly. So that's allowing those capacitors to build up slowly. Now, as that voltage gets to this point here, and you know that's at 55 volts or thereabouts, the BMS says, right, everything's all right. I didn't draw too much current. The voltage is perfect. It's time to switch on the main relay, the main positive relay, which I'll flash that one now, this one right here. You can see that one switches on, and boom, instantly we get that step up to the full system high voltage.
Very small overlapping time there, right?
Yeah, exactly. So at this tiny little section right here, the positive pre-charge and the positive main relay are on at the same time. When that system is there, when that's been achieved, the car says, okay, that's ready mode. And then it says it can switch off this pre-charge relay off. There's no need to have that going. So then we just have the negative and the positive going on at the same time until we get to the point where we switch it off right here. And then we can see the curving down here. This is the passive discharge. First part of discharge going down, and then active discharge really switching off quickly.
And we could have now a fault activated where active discharge is blocked or faulty, and then we would have the passive discharge, right?
Yeah, let's actually do that and see what that looks like. So we spoke about active discharge. Don't have a look at which number I'm using. This is the super secret pin code.
Still even can't remember.
So I'm going to switch on active discharge fault. And let's have a look at that again, see what that actually looks like. So I'll press my oscilloscope back here. So we'll go into ready mode so we can see how that switches on again. And see down here, now we're not seeing the active discharge at all. We're seeing this long passive discharge.
And this is what I think what we see back in the day when the car manufacturer said, like when there was only passive discharge, you have to wait for 15 minutes after you have shut down the high voltage system, right?
Exactly. So that's the, and this is a very fast version because we've got a very strong battery. We don't have large capacitors.
We don't want instructors to wait for 15 minutes and half of the hour is gone, right?
Exactly. So, yeah.
But it shows the idea behind it very clear.
Yep.
Nice.
Exactly.
Amazing, mate. I think that was a really good deep dive. Also, we saw on the one side how much the system offers, but also you gave us a good lesson basically on high voltage battery diagnostics. I think you can go on for hours, that's for sure. I mean, therefore we have the seminars and also further webinars will show up. After we have finished the webinar, you will get an email with the recording of it. We also will upload this to YouTube so you can watch it again or send it over to a colleague or whoever you think who should see that. And also, if you're now interested, you can ask for an offer. Just write us an email at contact@ln.eu. And there you can just ask for a CarTrain high voltage battery and that you want to get an offer. Then you will get this as soon as possible. Yeah, and for any other questions, we're still here, or feel free to write emails to us, to comment on YouTube under the video then. Then I think we will call it a lesson. Thank you very much for joining us today and being here and running through together with us through this deep dive for high voltage batteries. Have a great time and see you soon.
See everyone. See you in the next one.